Hi, I'm Chris Brown, and this is Module 2.10 in Intermediate Axiomatic Design, part of a course at WPI on axiomatic design and manufacturing processes. So for the next few minutes we're going to be looking at developing equations in the context of topographic measurement. And this is important in manufacturing as well, as it turns out, in pavements. And pavements for roads and for aircraft. So this goes back to a project that we had years ago, looking at the pavement for NASA for the problem of tire wear as the space shuttle lands. So commercial aircraft get many landings on a set of tires. Fighter planes tend to have under-designed landing gears and may get less than 20 landings on a set of tires. The space shuttle, they said, got about 0.6 landings on a set of tires. It started off with a 16-ply tire, and they were hoping to have 8 or 9 plies left when it finally rolled to a stop. So there was always a concern that they might have a blowout. And they did considerable testing on these, and they never had a blowout on this. Also, the nose gear is very light, and they would keep the nose up just as long as they could because the nose gear was even more undersized. And once this comes down, you can see you've got air pressure on the top of the wings, and the loads in the tires go up. But so here we can see the tire, the result of the tire being vaporized as it spins up on the surface. Of course, spinning up is one way of using braking, and so this is the spin up is a traditional way of braking aircraft. All right, so what we needed to do was to study the pavement. So we're looking at this interaction here between the tire and the pavement. And we're looking at a system designed for controlling a scanning laser profiler that will be used to measure the pavement. So they want to see if we could make runway textures that had high friction and low wear, and link the pavement texture to performance, both wear and friction. So there's a kind of special Axiom 1 question here. Can friction and wear even be decoupled on the same surface? Or if I increase the friction, do I automatically increase the wear? Alright, so step 1. So we have the customer needs. Now let's go to the FRs. So we need to assess pavement textures. To do that, we need some surface metrology system for pavements. Now a surface metrology system, for those of you who are not familiar with that term, should have at least 2 components. One for doing the measurement, getting a topographic map, essentially the surface, and another for doing the analysis. So FR1 and FR2 measure the runway texture in sufficient detail and then analyze the measurements appropriately. So we're decomposing FR0 in the context of DP0, a surface metrology system. So measure and analyze. We should note the constraints on this particular project. We had $20,000 available for components, and we had 6 months to get it operational, and the human resources, I suppose it's a way of recourses, but the human resources was one graduate student for a year and a professor for a month. So DP1, to satisfy the FRs, would be an adjustable texture measurement device, horizontal laser scanning system. Now it's important, of course, that it be adjustable because we're doing research and we need to be able to explore different sort of kinds of measurements. So we need an adjustable measurement system. And then we need a computational system for the analysis. So these are chosen, the diagonal or these DPs are chosen to satisfy the FR, so we can safely assume that we have an X there. But what about, say, DP1, the measurement system? Does that influence the analysis? Well, to a certain extent, yes. Because if the measurement system isn't working very well, we don't have a good enough measurement to analyze. So, and then, whoops, let's go back. Now the computational system that's doing the analysis, does that impact the measurement? No. So, so we have a triangular matrix, and so it's quasi-coupled or decoupled. And what it tells us is that we have to do the measurement device before we do the computational system. So the measurement will influence the analysis, both sequentially and physically. But this is the way the zigzag goes. And so we're going to look at FR1 and DP1, and we're going to look at this branch. So they are the FR1Js, these are defined in the context of DP1. So early in the research, we didn't know what was required of the measurement in terms of resolution or size. And the time to measure is also an issue. So these things need to be adjustable. We could say, so therefore they're all FRs in the control algorithm. But are they truly coupled? And how do we set these things without iterating? Well, let's take a look. So here is this measurement device configured for lab use on an air table with its large legs out. So there's a gantry system that's holding the horizontal scanning tables, and then there's one here for following the workpiece. And this is a triangulation laser position sensor. All right. So what does the measurement pattern look like? Well, it looks very much like kind of a milling pattern might look like. I might have even shown this in our last thing where we were talking about ball-end milling. So this looks something like the sole on that shoe that they showed us. So there's a couple things here. One is the sampling interval. That's the resolution in X. Excuse me. And the other, we're going to have the sampling interval resolution in Y. This is what we call the tracing direction, because this kind of instrument traces over, then indexes. Whoops, it's indexing over here. It traces over again and indexes and returns over here. So it traces in this direction and scans in the other one. All right, develop the FRs. So we need to provide for the adjustment of the resolution of the measurement, and provide for the adjustment of the size of the measurement, and provide for the adjustment of the time of the measurement. So what are the decompositions for resolution and size? And do we need another level in the hierarchy? All right, so step 4. So we have now control the resolution, control the measurement time, and control the measurement region. And we'll assign these variable names R, T, and M. So, collectively exhaustive, mutually exclusive, minimum number. Let's see. What are the DPs? Well, so here we've gone with a generic kind of thing. So a resolution control system, a time control system, and a region control system. So if we want to just look at axiom of the matrix, we've got DP1, resolution, resolution control for the system. And so that's going to impact FR1, but not the time for measurement, at least it's a first approximation, we don't know yet. So this diagonal matrix right now is expressing our optimism that we will be able to work these all out without introducing coupling. But as we've seen previously, this depends on the children. So let's take a look at the children now. So control resolution, we can do in X, Y, and Z directions. Control measurement time. So we can have the tracing time, the dwell time when we turn around at the end of each trace, and the number of traces could all be controllable for controlling measurement time. So then we can control the measurement region, and this is symbolized by M, and control of the measuring length and control of the scanning length. So now if we put all of these into the matrix, or into the decomp with our with the corresponding DPs, data acquisition and rate setting, distance between trace settings, sensor selection. So these are all in the resolution. Tracing speed, acceleration control, and number of traces are all in the time. And in the region control, it's still scanning length and the scanning length adjustment. All right, so let's start developing some equations. And so sometimes when we're looking at something like something that exists in a three-dimensional orthogonal space, the resolution that we're interested in is just each of those numbers squared in a kind of Pythagorean way to see what the total resolution would be. So this is a sum of the squares. So if we take a look at the time, what takes time? Well, we've got the tracing time, we've got the dwell time, and then we've got the number of traces. So we have an equation like this. So different form here. We're not adding up the squares. And then if we take a look at the measurement region, well, this is just the length in one direction versus the length in another. So here's the data acquisition. Here is the distance between two traces. Here is the high-speed resolution. Sorry, let's go back here where we were. Then let's see. So the number of traces shows up there and there. The tracing length shows up in two equations. The scanning length shows up in two places. And so obviously we have some potential coupling issues here. Here's a hint for developing the equations. Keep track of the units in the functional requirements, the DPs and the PVs. This will help developing the equations. So we initially have a matrix like this. So we filled in these off-diagonal x's based on our little analysis there. And now we want to check for inheritance. So here's where the children are from DP2 to FR1. And we have one peg there. Here are the children of 2 up here with a parent of 1. So these are children. These are children parent. So this x needs to be promoted, and there's another x on the other side over here, which we'll get to in a moment. So here's the inheritance. Let's see how this goes. So we start off and we put an x here and then another one there. And so this is the upper level coupling now. But there's 2 x's added. And then we have another one like this. And again, there's 2 x's added. And then we have another one for down here where the coupling was. And so in this, virtually every time there's coupling, we need to promote it to the parent level. And so here the promotions are all circled. So when we collapse and look at just the high level interactions now, we have an upper triangular matrix. So we could reorder and renumber, and Claro does it for us like this, and goes for a lower triangular matrix, which is only slightly confusing because we flip these things around, and so we recognize that often we go into something like this. Let's put the thing that's most important to us on the top, but in reality it doesn't matter. And then when you rearrange the matrix, this is what you're going to get. So anyway, let's take a look at some things. Here's a pavement actually measured by that instrument, and it's a skidabrator as a way of conditioning your runway pavement to get around the lower friction coefficients that you might see as the rubber material fills in the details on the pavement where it lands. So here is virtual tiling. So here we're trying to tell how quickly can we tell something about the surfaces. And so here is a relatively large scale where we're looking at some of these surfaces. And then here's a finer scale and a finer scale. So we do this in a triangular tiling method, and then we plot the relative area, and the relative area is the tiled area divided by the projection of the surface. So so we can see in the projection, we can see there's some little bits that are left over here, and those were not covered in the tiling exercise. So when the tiling exercise finally gets to this border, it can't fit a full tile on, it leaves a little thing blank. Anyway, so we can portray this as a relative area versus the scale. So this is a kind of multi-scale analysis. And we can take a look at the predicted friction coefficient with the actual one, and the predicted one naturally does a lot better. Now here's something to answer the question about wear and the friction. So we plot wear on one axis and friction on the other axis, and the surfaces all can fall in some place. Whereas it always seems to be below some diagonal here. So in this case, yes, we can independently adjust wear and friction. And I remember the graduate student who was working on this was a little disappointed because he was looking for things to fall in a straight line. But if we take this point out here, this has got a high friction coefficient, but a relatively low sort of wear rate over here. So this would be a good surface for high friction and low wear. Surfaces up in this region are high friction and high wear, or maybe the kinds of things you'd like in grinding. All right. So that shows the development and assigning of X's and O's in the matrix and some quantitative work. So let's just see how this ended up. One of the things is the order of adjustment of the DPs that we found was not intuitive, at least for me. And the design project is part of a whole one that has allowed us to successfully predict friction on runways at NASA Wallops facility. And no other research group has been able to find such a high correlation between friction coefficient and pavement. Thank you very much for your attention.